eating round pegs, scale holes, why GPGPUs are not an architectural mismatch for modern LLMs. The same round pegs do not fit scale holes persists because it captures a deep engineering reality. Inefficiency most often arises not from the flawed components, but from the misalignment between the system's assumptions and the problems it is asked to solve. A scale hole is not a poorly made, it's simply optimized for scale pegs. Modern large language models (LLMs) now find themselves in exactly this situation, although they are overwhelmingly executed on general-purpose graphics processing units (GPGPUs). These processors were never shaped around the needs of enormous inference-based metric multiplication. GPUs dominate not because they are a perfect match, but because they were already available, massively parallel, and economically scalable when deep learning began to grow, especially for training AI models. What follows is not an indictment of GPUs, but a careful explanation of why they are extraordinarily effective when the workload is rather dynamic and unpredictable. Such a graphic processing and disappointingly inefficient when the workload is essentially regular and predictable, such as AI LLM inference execution. The inefficiencies that emerge are not accidentally, they are structural, predictable, and increasingly expensive as models continue to evolve. Execution geometry and the meaning of the square. When a GPU renders a graphic scene, it deals with a workload that is considerably irregular at the macro level, but rather regular at the micro level. A graphical scene changes in real time with significant variations, content changes in the triangle and illuminations. But in an image, there is usually a lot of local regularity. One frame displays a simple brick wall, the next the explosion creating thousands of tiny triangles and complex lightning changes. To handle this, the GPU, the architecture relies on a single instruction multithread SIMT or wave warp based approach where all threads in a wave and warp, usually between the 16 and 128, receive the same instruction at once. This works rather efficiently for graphics because while the whole scene is a mess, local patches or fixers are usually doing the same thing. This allows the GPU to be a micromanager, constantly and dynamically scheduling these tiny waves to react to the scene chaos. However, when applied to AI and LLMs, the workload changes entirely. AI processing is built on a tensor match and matrix multiplication, which is fundamentally regular and predictable. Unlike a highly dynamic game scenes, matching math is just a immense but steadily flow of numbers. Because AI is so consistent, the GPU fancy, the high-speed micromanagement becomes unnecessary. In this context, the hardware is just overhead, consuming power and space for flexibility that AI doesn't actually use. This leaves the GPGPU in a bit of a paradox. It's simultaneously dynamic and not dynamic enough. It is too dynamic because it wastes energy on a micro level, programming and complex scheduling that a steady AI workload doesn't require. Yet, it's not dynamic enough because it's bound by the legit size of each wave. If the AI math doesn't perfectly fit into a word forward 32, the GPU must use padding, effectively leaving seats empty on the bus. While the GPU is a perfect match for solving irregular graphics problems, it's an imperfect fit for the sheer repetitive scale of the modern tensor processing. Wasted area as a physical quantity. This inefficiency can be understood geometrically. A circle inscribed in a square leaves about 21% of the square area unused. In processing hardware terms, the area corresponds to execution lanes, cycle and bandwidth and joules, and any portion of these reduced resources that performs work that does not advance the modern models of this wasted area. The utilization gap, MFU. The primary way to quantify this inefficiency is through the model flows utilization MFU. This measuring measures how much of the chip's theoretical peak path power is actually being used for the model's calculations versus how much is wasted on overhead, data movement, or idling. For an LLM like GPT-4 running on a GPGPT-based accelerators operating in interactive mode, the MFU drops by an order of magnitude with the hardware busy with the bookkeeping, which encompasses moving data between memory levels, managing thread synchronization, or waiting for the next wave of instructions to be decoded. The energy cost of the flexibility. The inefficiency is even more visible or power consumptions. A significant portion of that energy is spent powering the dynamic micromanagement, namely the logic gates that handle warp scheduling, branch prediction, and instruction fetching for irregular tasks. The padding penalty. Finally, there is padding inefficiency. Because of a GPGPU-based accelerator operates in fixed wave sizes, typically 32 or 64 threads, if a specific calculation doesn't perfectly align with those multiples, often happening in the attention mechanism to the LLM models. LLM models, large language model. Mode. And the GPGPU still burns the power of full wave while some threads set idle. These effects multiply rather than add. A GPU may be promoted with a high throughput, but once deployed may deliver only a fraction of its peak useful throughput LLM inference, while drawing close to peak power. The memory war and idle compute. Even if compute utilization was perfect, LLM inference would still collide with the memory war. The growing disparity between how fast processors can compute and how fast they can access memory. LLM inference has low arithmetic intensity, meaning the relatively few floating point operations are performed per byte of data fetched. Much of execution time is spent reading and writing the key value, KV cache. GPUs attempt to hide memory latency using massive concurrency. Each streaming multiprocessor SM holds many warps and switches between them, while others wait for memory. This strategy works well when memory accesses are staggered and independent. In LLM inference, however, many warps store simultaneously while waiting for similar memory accesses. As a result, SMs spend a large fraction of idle time, not because they lack instruction, but because data cannot arrive fast enough. Measurements commonly show the 50 to 70% of a cycle during inference are lost to memory stores. Importantly, the power draw does not scale down proportionally since the clocks continue toggling and control the large remains active, resulting in a poor energy efficiency, predictable stride assumptions, and the cost of generality. To maximize bandwidth, GPUs rely on predictable stride assumption, that is, the expectation the memory accesses follow regular patterns. This enables techniques such as cache line, coalition, and memory swizzling, the remapping of the addresses designed to avoid bank conflict and improve locality. LLM memory access patterns violate these assumptions. Accesses into a cave cache depend on token positioning, sequence length, and request interleaving across users. The result is reduced cache effectiveness and increased pressure on address generation logic. The hardware spends additional cycles and energy rearranging data that cannot be reused. This is often described as generative tax. Why GPUs still dominate? Given these inefficiencies, it's natural to ask why GPUs remain dominant. The answer lies in history rather than optimality. Early deep learning workloads were dominated by dense linear algebra, which mapped reasonably well onto GPU hardware. Training budgets were large enough that inefficiency could be absorbed. Inference changes priorities, latency cost per token, and energy efficiency now matter more than peak throughput. At this stage, structural inefficiencies are no longer abstract. They directly translate into operational cost. From adapting models to aligning hardware. For years, the industry focused on adapting models to hardware, such as larger batches, heavier padding, and more aggressive quantization. These techniques smooth mismatches but do not remove it. A growing alternative is architectural alignment, building hardware whose execution model matches the structure of LLMs themselves. Such design schedules work around tokens rather than warps, and memory systems optimized for KV locality instead of a predictable stride. By eliminating unused execution lanes entirely, these systems reclaim the wasted area rather than hiding it. The inefficiencies seen in modern AI data centers are idle compute, memory stores, padding overhead, and excess power draw are not signs of poor engineering. They are the inevitable result of forcing a smooth, temporal workload into rigid, geometric execution models. The GPU remains masterfully engineered square holes. LLMs remain inherently round pegs. As AI becomes a key ingredient in global infrastructure, the cost of this mismatch becomes the problem itself. The next phase of AI computing will belong not to those who shave the peg more cleverly, but to those who reshape the hole to match the true geometry of the workload. Laura Riccati is a business advisor to Sora, a technology company offering silicon semiconductor solutions that redefine performance. As a noted chip design verification consultant and industry expert on hardware emulation. Okay, today I read this article, The Round Pegs Scare Holes, Why GPGPUs are not architectural mismatch for modern LLMs. Thank you for your time. See you next time.